Welcome to the Level Up Life podcast. I'm your host, Scottie Hobbs, where we're here to remind you that your family's your most important work, help you feel better, and learn how to earn more income for your family. I'm here with my friend, Dr. Mark Bartlett. Mark is the Chief Scientific Officer with Make Wellness, a PhD immunologist, a research and development scientist. He started his career in the National Cancer Institute and has since dedicated his life to helping the body function better with natural solutions. We're going to talk a lot about nature, the body, and especially peptides. Mark, welcome to the show.
Yeah, Scotty, it's great to be on with you. Well, as your viewers will probably see very shortly or hear very shortly, I have a funny accent. So south of the border, like way south. So I'm from Australia. I was raised out in the country there. And, even Australians appreciate how weird it is down there. Like you've got every animal has got a pouch. You've got like deadly spiders and snakes, and it's just nasty. And even the plants are very different, right? All the gum trees, and did you know you can't even get shade under a gum tree because the leaves hang down to conserve water? So it's the middle of the day, you get under a tree, and like you're not even in the shade. And I think that that's what shaped me, like just made me really fascinated in natural science. And so eventually I just sort of followed my path of curiosity and just kept studying. I was a perpetual student, studied biochemistry, was really interested in natural products chemistry. So did chemistry and then realized, wow, like you can synthesize these things, but plants do it better. And so my master's was actually in plant carbohydrate chemistry and photosynthesis. So how the power of the sun and how plants pull CO2 from the atmosphere and build all of the molecules of life, whether they're like odorants or like bioactives. That sort of led me into a little stint in cancer research and immunology, and then realized, man, I should do a PhD. Like, just let's go all out. So, did a PhD in immunology and studied autoimmune disease and cancer metastasis. That led me to the National Cancer Institute up the road in Washington, D.C. And but you know what kept tugging at me was this concept that plants do it better. And that drugs and the drugs that I was studying for cancer and for immunology are they usually have in their roots like a natural product somewhere. Give you an example. If you've got back in the old days, if you had a disease, then the people would say, well, you need to find a plant that is associated with that condition. And so back in old England, they'd say, well, I've got rheumatoid arthritis, I've got lumbago, like I'm feeling stiff and sore. And they'd say, well, we need to look where that happened. Let's look in the sort of the damp, swampy areas. And they found the bark of the willow tree and they made a tea out of it. And like, lo and behold, it works. It's like, what? How does that work? So there are salicylic acids in the bark. So this is a natural product that's kind of a natural anti-inflammatory, right? And then the Germans got a hold of this. They're all the chemists over there, right? And they're like, well, if we modify it a little bit, maybe we can make it more potent. So they added an acetal group, just a CH3 group to it. And that's called acetyl salicylic acid. That's aspirin. So there's a really good example of how you've got like nature makes the molecule, man modifies it, makes it more potent and sometimes more toxic. So here I am at the National Cancer Institute and sort of looking at drugs for, cell-cell communication and drugs for cancer. And I'm like, yeah, but nature does it better. And I had this epiphany. I still remember this to this day. Like, what if instead of sort of using the drug once you're sick, like find the origin of that drug in plants and just like eat it every day and don't get sick? Like, wouldn't that be novel? And I still
Wow.
remember when that happened. And so I was getting ready to leave the National Cancer Institute and sort of follow that. And I thought, where? How? And the phone rings, and it's this company in Utah that's a natural products company and said, hey, we heard you're doing some good stuff up there. Would you like to come and look? And I said, I'm sorry, I don't know anything about soap. And they're like, no, no, no. We have this natural products division, and we really need a scientist to sort of head up the R&D. And so, long story short, that's what I've been doing for the last 30 years is just kind of going this natural route. And that's, I've sort of followed my heart and a little bit of a calling, I suppose. And sort of for a little while, I was looking at, essential oils and the power of aroma to change your health. And then it sort of feels like I've come full circle because peptides are where I started, like these natural products in immunology, all those signaling molecules are peptides. So like I'm super excited to be here in this sort of home stretch of my journey in this area of peptides.
I love that. Man, there's so many questions I want to ask to unpack. Like I want to know more about you and I want to know peptides because I'm someone that deeply wants to help people find a calling in their life. So when you said that, I'm like, we got to talk about that a little bit. So let's talk about that a little bit. How do you think someone finds a calling? Like what does that mean to you? Because I think a lot of times people pursue a job that might pay the most or might give them the best benefits or that feels the most secure. Doesn't sound like you
Yeah.
really went that path. Like,
Yeah, I would, I've thought, well, you know what, I can't say that I'm pure in that regard. Like, okay, so first of all, I just said, college is for bludgers, mate. I'm not going to go to college. Like, that's all for the eggheads and stuff. I'm just going to be an honest plumber or something.
yeah,
And then I came to America to do some, I guess you could loosely call it missionary work. It was refugee resettlement work in the early 80s. We had all these refugees coming over from, um, war-torn countries, Cambodia and Laos and the Hmong that live in the hill tribes of Laos. And so I ended up in the streets of Salt Lake City learning to speak Laotian and Cambodian and Thai and sort of helping these guys. And my flatmates were these well, they were very different to me. I'm this Aussie sort of country guy, blue collar, and Americans are just so different. Like they're very motivated. The sky's the limit. Like they don't put limits on themselves. This was
yeah,
my experience. And I remember one of my roommates said, "Well, hey mate, what are you going to be when you grow up? Like when you stop doing this refugee resettlement stuff?" And he said, "I'm going to be a surgeon." I'm like, "A surgeon? Who the crap do you think you are, man? Like that the surgeons are for like I don't know, famous people, not for you and me." He said,
yeah,
"No, no, I'm going to be a surgeon." I thought the audacity, but then it was like, but wow, like here's a guy who has confidence that he can do anything that he wants. And that changed my life. And I went back to Australia and like coming from sort of a family of country people, nobody had a degree. My mother didn't even finish high school. My
yeah.
grandmother couldn't even read and write.
Wow.
So we were like back hills, like, log cabin stuff. But that sort of changed my view of what was possible. And so I said, I'll go to college. What'll I study? I didn't even know what half the careers would be, but I thought, well, I'll study. I really like science, right? Going back to venomous snakes and koalas and pouches and things. I'll study science.
Yeah.
And but I thought if I do that, I'm going to be rich because these people that study and get degrees are going to be rich, right? And I do remember my molecular genetics professor, Professor Delgado, and he drove this like beat up old sort of baby blue colored Volvo station wagon, and I was like, oh my gosh, like I love him even more. Like as filthy rich as he must be because he's got a brain the size of a planet and he knows genetic engineering, he's humble enough to drive this like sweet little old 30-year-old like car that's all just about ready to break down. Like what a humble guy. And then I finished my degree and I was ready for the big bucks to roll in, right? And my first job was at a cancer research unit in a hospital. And they said starting salary 16,500 a year. And I'm like, but wait, but wait. The guys in the dock that are loading boxes onto the truck, they're getting 17,500 a year. Do you mean to tell me that I did like all this work and got like first class honors and a master's? I get that. They're like, yeah, welcome to the club, mate. That's what they pay scientists. So then I realized maybe I'm being a bit hypocritical. Then I realized, okay, it's not about the money, it's more about the calling. So, but I guess to answer your question, I still believe very firmly that you should follow your passion, that it shouldn't just be about like what's in it for you. Like and I think most of us, I heard the other day that the two most important events in your life are one, being born, and two, learning why you were born.
Yeah.
Right. And I think that's really important, whether it takes prayer or circumstances just sort of point you in that direction and you hear the universe calling. I just am so glad that I sort of chose to follow my heart rather than just like, where's the money?
Yeah, that's beautiful. When I chose my career path, I was like, I'm gonna go to BYU, Idaho. It was Rick's college at the time.
Yes.
And I was like, I'm gonna be some sort of doctor of some sort because that's gonna make good money. And I
Yeah.
was like, I'll be an orthodontist because I had braces and headgear and all the stuff, and it changed my life. Maybe I'll go change some other life. But I had no desire to be in someone's mouth. I didn't even think that through. And I was like, I did not like the classes. It was not my place, and I didn't love it. And then I went on to be a dental lab technician. I was like, oh, I like art and I like to draw and be creative. So I'll go create teeth, like crown and bridge.
Yeah.
So I went to a tech school. It was like $15,000 for 10 months or something. I was like, I can endure that. And I got a job. And after 2 years, we had our birth of our first daughter. I was making $11 an hour, no insurance. And I asked for a raise, and he was like, you're not quite, you're not worth it yet. And I'm like, well, can I
Wow.
get
Yep.
insurance? He's like, well, I was going to pay you $10 an hour, but I gave you 11 so you could get your own insurance. And I was like, and I did not like it. I did not like sitting. It was just me and two other guys. And I just sat in the back in a glass box with like goggles on, grinding gold and silver.
Yeah, you could have got yourself some tips, like just keep the shavings and it builds up over
I
time, right?
know. And I was like, this is not how I want to spend the rest of my life. But it's funny, then I came up, someone introduced me to workouts and nutrition, and I fell in love with
Yeah.
nutrition and health and that changed my entire life. So that's my calling came over time. It
And
didn't,
not only
yeah.
change your life, but it changed your life because you're using that to help others, right?
Yeah.
That's yeah.
Using it to inspire others and help other people on that journey. So I love that you shared that with us. And here you are today. So what is your role with the company Make Wellness? Then I want to ask some questions about peptides in general. Like,
Yeah, I'm the Chief Scientific Officer here at Make Wellness, and it's a really unique company. It's a startup, right? We've only been going for a year, um, and it's kind of interesting because that first place that I went after the National Cancer Institute, I was there for 27 years,
wow.
and we're actually doing some pretty cool stuff. And I love doing research. You could ostensibly call this like a product-oriented industry, right? We make vitamins, we make minerals, we do something for a workout, we do protein shakes. So you kind of maybe view that as, oh yeah, like, that's just product development. Like anyone can do that. You put the ingredients together, you sell it, either online or direct sale, right?
Yeah.
For me, it was much more than that. It was okay, other people are doing other stuff, but what can we do that can really break through? Like, what is not like what's hot right now, let's do that, but
Hmm.
what is the science telling us is hot right now? Let's look for clues there. Because I mean, that's innovation, right? That's where, and it's not just innovation for its sake, but it's to sort of break through and find out, like what's important. So I'll give you an example of sort of what drove me. 30 years ago, this concept of free radical biology was very new. In fact, it was nearly 40 years ago that I bumped into this concept, and there was this proponent, a scientist called Lester Packer at Berkeley University, and he had this like breakthrough thought, like nobody else had actually considered this, that you have subatomic particles that actually change the biological state. That was always considered to be sort of the realm of physics, and biology is just one molecule bumping into another or a receptor and things happening. And he was saying, no, there are unstable chemical entities called free radicals, and when they're short an electron, they're going to steal that electron from electron dense parts of the body, and
Mm.
that would be the cells and the DNA, and therefore damage the cell membranes and the DNA. And that was like, Scotty, you've heard of this, and I bet everyone in
Yeah.
your audience has heard of this. But 30 or 40 years ago, this was almost like heresy. It was like, what? That was almost as bad as being a chiropractor back then, right? It
Yeah.
was like, this is crazy. And then this journal started called, yeah, and on free radical biology. That fascinated me back in the 80s. And I was like, this is incredible. Like we are learning. And again, by the time I'd finished at NIH and started working with this company in the 90s, this was still a relatively new concept and nobody really understood what it meant. But we were starting to understand that the plants again had the answer. Right, the colorful molecules in plants, the carotenoids, the polyphenols, they were actually able to mop up these chemical entities, these free radicals that were short electrons. So that's kind of what I focused on. And what I loved is there was this barrier to entry. Like people didn't know. You'd say free radical. They'd say, "What's that?" And then you say, "Oh, well, if you can get the knack of explaining it in a simple way, people suddenly realize how important it is." And
Hmm.
now it's like it's really common knowledge, right?
Yeah.
Um, that's so about 27 years into that, some family situations happened, and I just said, I'm kind of done there. I quit that job. And my wife's like, "What are you doing?" Like, "Well, you're earning enough with your real estate now, aren't you?" So she said, "Yeah, but who's going to pay for your race car and your race bike?" I'm like, "Well, aren't you?" She said, "Nobody." Go get a job. So I thought I was done. But then
Okay.
the phone rang again, and it was like, it felt like a calling again. And I was actually found myself in the most woo-woo area of science you could ever imagine, which was essential oils. And again, it was like, okay, I could just like do blends and sell them because they smell pretty, or I can dig into the science. And I did. For 3 years, I dug into the research of that and looked at the olfactory bulb and these olfactory receptors and how they work and how they interpret the signal and where that goes in the brain and how that signals the brain to remember or to get sleepy or to wake up or to be less stressed. There's a lot of science there. And then ultimately, I can't even remember the question now. I'm just rambling. But
No, I like it. I'm learning.
so then I get a call from the CEO that was at Nu Skin, and he said, "Hey, we're starting something new. Have you ever heard of peptides?" And I was like, "Yeah, that kind of brings me back to my early immunology days. Like peptides are the molecules, they're small protein entities, right?
Hmm.
They are directly encoded for by the DNA. The DNA blueprint is essentially for proteins and peptides. And these peptides are the communication molecules in the body. This is the direct way to communicate. So even though I'd focused on sort of biological actives, what those do is they sort of trigger something, maybe, but ultimately they end up sort of triggering DNA to make a peptide or triggering a cell to communicate with another cell, which is via peptides and small proteins. So I said, "Well, yeah, Truman, I'm interested in that. But, here's the thing. Like, this concept of peptides and these communication molecules has really just been what I call observational biology, meaning we know what's going on,
Hmm.
but we're not interfering with it. We're just saying, oh, that's how cells communicate. Okay, when a bacterium invades your body, then there's a macrophage that says, hey, I've got a receptor for like there's something in the bacterial cell wall, like that's gonna like get me really excited, and I'm gonna send out these messages. Like I'm gonna recruit the T cells and the B cells, and then you have this cascade of immunological activity. That's observation, right? What I mean is, but you don't mess with that. And then I thought to myself, well, wait a minute, like insulin is a peptide. It was discovered 100 years ago. They didn't quite know what it was back then, but they knew that it sort of helped with blood glucose control and it saved people's lives.
Yeah.
But not much has actually happened since then. And then I remembered, wait a minute. Like there's this new drug called Ozempic that is like was ostensibly to sort of help with diabetes, but seems to curb appetite dramatically. That's a peptide that's injected, it's synthetic. Um, this is why people are interested in peptides. Um, and so, yeah, the concept of make wellness is not sort of this drug route, but rather the acknowledgement that once again, nature has peptides in the foods that we eat. And generally, we don't feel their effects, even though they're there. What can we do to find the peptides in nature? In the same way that I was doing sort of after I left the National Cancer Institute, can we find nature's equivalent to these drugs? And that's pretty much inspired the drugs, right?
Mhm.
And then, because this is a much more gentle approach and it is safety through evolution. And I just really like that approach rather than the drug approach. So once again, like this opportunity opened up to help people in like this new frontier that reminds me a lot of what happened with the free radical biology revolution 30 years ago. There's a bit of a barrier to entry for people's knowledge, but this is just an incredibly meaningful space right now.
Yeah. I keep hearing this answer of the answers in the plants.
Yes.
So I love that. So What is so maybe someone right now they've heard of Ozempic or they had no idea that insulin was a peptide. What's the difference between a synthetic peptide or like Ozempic and a natural peptide like what Make Wellness has, a bioactive precision peptide? What's the
Yeah,
difference?
I love that question because this will unleash at least an hour of pontification from me. But sort of to help you understand that, let's go back to what happens in the body.
Yeah.
Like we're always hungry. Humans are always hungry. Are you like me? I'm always hungry. Like I can just eat like at Taco Bell or at Los Hermanos, and I've just had this big meal, and then I get home and what do I? Sometimes I actually literally open the fridge and go, "What's in there?"
What's in here?
That's crazy. Humans are driven by sort of these instincts, and you kind of wonder where do they come from? We need to
Mhm.
love, we need to connect. That's actually through peptides, right? It's oxytocin. We grow muscle, we lose muscle. Those are peptides, right? Like myostatin that says, hey, if you don't need the muscle, drop the muscle because it's too expensive to maintain. Hunger is also driven by peptides. And let's say you're hungry and then you eat some food, then that those macronutrients, basically protein, carbohydrate, fat, right? They're in your GI, and there are cells in the gut lining called the L cells and the K cells, and they sort of detect the macronutrient, and their job then is to produce this peptide called glucagon like peptide 1. And there's another one, GIP, right? So GLP-1. Let's just focus on GLP-1. So that's a peptide that the L cell releases into the bloodstream, and it goes to the brain and it goes to the pancreas, and it kind of says, okay, food is here. Step one, brain, turn off your food-seeking behavior, and then step two, hey, gut, slow down. Like gastric emptying needs to slow down because you're going to be churning and digesting, and pancreas is going to release a little bit of insulin. Like it's amazing.
Mhm.
But I have a question for you, Scotty.
Okay.
How long, like the L cell makes that peptide, the natural GLP-1 in your body,
Okay.
how long does it last before it's broken down? Do you know?
I have no idea.
Yeah, like I was actually at a
Like
conference in
no idea.
Berkeley a couple of weeks ago. Well, don't be ashamed because like I asked a whole bunch of doctors at this meeting and they didn't know either. It's not common knowledge, but that peptide lasts about 2 minutes before half of it's gone. It's called the half-life.
Mhm.
And then after 4 minutes, like three-quarters of it's gone, right? Because it keeps halving. So we call that a half-life of 2 minutes. And this is how nature works. It produces the signal, and then there's a decay, and it has to reset the signal.
Mm.
Imagine if it lasted longer than that. Like, yeah, that'd be great because I would stay full longer and I wouldn't be opening the fridge after I just ate a meal. But this is survival. Like humans were designed to live in like a time where food is scarce. Like humans just had to be driven by hunger because they had to either hunt for it or farm for it. And like if you didn't think about it, if your body didn't warn you ahead of time, you'd probably starve and die of malnutrition before you got food. So this is the signal, but it's broken down, it's recreated, right? So if you eat food, the signal lasts for a while, it's broken down. This is the pattern of nature. So now you ask, what's the difference between, say, one of the drug, GLP-1? They call it a GLP-1 receptor agonist, meaning that it's like um, it does the same thing, but this one's synthetic, right? You inject it. Okay, what's the difference? These GLP-1 drugs, or sometimes done by compounding pharmacies, are completely synthetic. So what happens is you look at the structure of, say, GLP-1. It's probably more complex than this, right? It's a string of amino acid residues, and it's like a key. And
Okay.
maybe this pink one here is a positively charged amino acid, and maybe this brown one is negatively charged, and maybe the green one is hydrophobic, meaning it hates water, and maybe this dark green one is hydrophilic. Either way, that's like a key because of the different amino acids that are in that sequence, that perfect sequence. It is like the key that unlocks your house. And you've frozen. I hope I'm still
No, you're
going
still
here.
talking.
It's like a key. And so, okay, good, good. So from nature, here's the key. Okay, let's synthesize this, And what we say is, well, okay, we've managed to synthesize it. It's identical to nature, but it's going to get broken down really fast. There are enzymes that break it down, right? So let's play around with it a little bit. Let's do an amino acid substitution, and you can do this. So we take out
Okay.
this green one here and put in maybe a pink one, and let's see if that one still works. Does it still work? Oh, yeah, it still works. Does it resist degradation? Yeah, somehow now the enzyme doesn't recognize it. So by playing like that, even with amino acids that aren't proteinogenic, meaning they're not even natural amino acids, they can configure basically a synthetic version that doesn't die in 2 minutes. So here's the next question for you, Scotty. How long does Ozempic last in the body? What's the half-life?
Man, these are great questions. I have no
And
idea.
the answer is 1 week.
One
So
week.
it's lasting a week. Yeah. So imagine what that's doing because it's very potent and it's hammering those receptors saying, hey, so there's food in the stomach. So the stomach needs to shut down, but there's nothing in it. And it's saying, hey, you need to stop eating. And so you're not getting the protein that you need. So your muscle gets the message, hey, there's no nutrients here. So it's time to sort of secrete another peptide called myostatin and break down the muscle. So you can see that the synthetic approach is very powerful, but it's also quite unnatural and leads to, just like any drug, a lot of side effects. But I'll throw in another example. Like when you sleep, when you're in deep sleep, and only when you're in deep sleep, your body, a certain peptide messenger called growth hormone releasing hormone, sends a message to the pituitary to release. It says that my internet is unstable. I don't know why. I'm in a landline here, but
No, can you hear me?
well, we're on a roll there for a bit, but I'm not sure how we are in terms of our bandwidth.
No, you're good. Are you there, Mark? Can you hear
Yes.
me? Okay.
Yep.
And I'll edit out when I can edit out when it paused there.
Yeah.
So you had a really clear connection all the way through you explaining the 1 week half-life. It was
Oh, good.
all very
Good.
clear. Yeah. So I'll just edit out and then I'll bring it in back in right here.
All right.
So you were going to talk about something else and then you can just start right there and I'll cut it in.
Okay. Yeah. So there's another example from nature, right? And that is how the muscle gets the signal to grow. And what's really interesting is that the biggest signal comes while you're asleep. So there's a sleep architecture, but there's this part of sleep called deep sleep, slow wave sleep. It happens a couple of times during the night, especially in the early part of the night. It's only during that slow wave sleep that there's a message to the pituitary by something called growth hormone releasing hormone. Kind of sounds redundant, but what does it do? It helps the pituitary to release growth hormone. And that goes to the muscle, binds to receptors on the muscle, and it's a peptide and says, hey, muscle, you can grow. And as long as it's got that other receptor that says, hey, there's plenty of amino acids here, like you've been eating protein, then the muscle will have permission to grow. There are synthetic peptides that do the same thing, right? So inject the peptide, get ripped. I think there's a cautionary tale there, though, because the body, like I said, is supposed to present the message, and then the message decays and it has to reset the message. I think there's a reason why this only happens during those brief periods, like maybe an hour or two at night, that you get the message, because it goes through that signal binds the receptor, and then it has to go through this junction box called mTOR, and it's the mammalian target of rapamycin is what the name of that mTOR thing is. So it's like this junction box. And that junction box also receives a message from the nutrient receptor and it says, okay, okay to build muscle. Sends a message to the nucleus and the DNA is transcribed and translated and protein is built. Here's the catch. That mTOR is also responsible for orchestrating the cleaning of the body. So when it's at rest, when it's not being sort of hammered by the nutrient receptor and the growth hormone receptor building muscle, it rests and it sends a signal to the rest of the body. Time to do immune cleanup. Look for any cells that look like a little bit suspect, any cells that look cancerous, or any cells that look damaged or virus infected, any debris, clean it up. And so you can imagine with a peptide that has a really long half-life and like the CJC peptide 1295, is it? That has a half-life of 6 to 8 days as well. So
Okay.
you're not letting mTOR rest. And that's why they often say, yeah, you need to let this peptide rest a little bit. You should sort of go off it for some time. That's part of the reason is because we don't know what the long-term effects are of chronically upregulating mTOR, which is in that junction pathway. So that's why I love the natural approach. I love finding peptides in nature. They have a half-life that's kind of similar to nature. So they help your body, they whisper it to it, they coax it along, but you don't have that risk of sort of overriding the system.
Okay, I have a quick question on that. I have a couple of questions that are on my mind right now. So I have people that come to me like, okay, is this like BPC 157? Like they're looking at fit peptide to grow muscle.
Right.
And so what you're explaining there is
Yes.
the big, obviously one is synthetic injectable, um, and the half-life. Do you know the half-life on that one? It's okay if you don't. Is it longer?
No, I don't offhand. Yeah, I'm not sure offhand, but yeah, that's a good question though.
Yeah.
BPC 157 is a really interesting peptide because it was actually originally isolated from the gastric juice of humans, I think. So
Okay.
it's something that exists in the GI. And actually, I think that you can take it orally, which kind of makes sense because some people think, oh, a natural peptide that you take orally, it's like, you don't be ridiculous. Like
Hmm.
the gut is like this nasty, I mean, the stomach is just full of acid, like pH 2 or 1.5. It's just like battery acid. There's no way that a peptide will survive there. And then, it gets dumped into the lower part of the GI where you've got now all of the enzymes that are designed to break down proteins and peptides. And so how is it ever going to survive? Well, it's interesting because we find peptides in the GI. BPC 157 is an example. And it's kind of a healing peptide, right? Maybe it helps heal the GI and they are injecting it into sort of sites of injury and it helps sort of help with the sort of speeding up healing.
Yeah.
There are other peptides from nature too, like when babies have their first milk, colostrum is full of these immunogenic peptides that survive the GI. So it is about the structure. There are structures of peptides that make them fairly immune, but also when you get them from nature, they're usually chaperoned with a whole bunch of other proteins and peptides that kind of protect them through their journey to the receptor.
Okay.
So I don't know what the half-life is of the BPC 157.
Yeah, that's a great answer, and it led into what my next question was. Is I had a conversation just yesterday where they're like, "This sounds great. Like, I love the idea of plant-based, natural peptides extracted from nature, but." And they were very firm on you cannot get a peptide through the digestive system, so it's not going to be effective. So maybe
Yeah,
they were like, okay, maybe
yeah.
you guys there was all this research and they did find it, but I need you to tell me how it's getting in and doing what it's supposed to do. So what would be your answer to that? How do these natural peptides do that? And you kind of went through it, but I'd like
Mhm.
a
Yeah,
good
maybe in a
solid
little
answer.
more detail.
Yeah.
Yeah, I mean, you're absolutely right, Scotty. Like this is the number one thing that people who are educated in this area will say, like, wait a minute. Like this doesn't make sense. Like why have they been injecting insulin all these years? Like if it really worked orally, we'd be taking it orally, right? Why are these therapeutic peptides and things like Ozempic and stuff are they injected? Well, everyone knows it's because it has to be injected because otherwise, because that bypasses the GI, which is just so caustic and degrades the peptide. So most of the question that we get comes from this perspective that medicine is doing it a certain way, and
Hmm.
therefore that's the only way, and anything else kind of defies biochemistry. So we get this all the time. I usually start by giving the example. Well, wait, but how do you explain colostrum peptides? How do you explain that there are peptides in milk? Like if you drink a liter of milk, there's a peptide in that milk that makes you sleepy. Like, how does that work if it gets destroyed in the gut? We've known about that peptide for decades, right? And there are some popular products that sort of isolate that, and it's part of their kind of sleep formula. So when that happens, you kind of start to scratch your head and say, well, wait a minute, there seem to be exceptions. So how does that work?
Yeah.
And so this is important. I talked earlier about how in a peptide you've got like all sorts of possibilities. And you think, okay, you dump that into acid. Well, you know what? Some they don't all break down. And and then you dump it into sort of a pool of enzymes. Well, guess what? The enzymes have to obey rules too. So the main enzyme that breaks down GLP-1 is called DPP-4, and it's a dipeptyl peptidase, right? Number four. And it's a peptidase. It's an enzyme that can count. So its job, it says, okay, here's the first amino acid residue. Here's the second one. I'm allowed to chew here and only here. Like enzymes are incredibly specific. They
Wow.
only catalyze one chemical reaction. They have a mouth that's a certain shape and it can only do one thing. Or maybe there's another enzyme that only chews up where the leucine is, or and so on. So they obey certain rules. But there are certain shapes of peptides and proteins where they might be cyclotized. There may be these what's called these cysteine bonds that form a bridge. And so, depending upon the structure of the enzyme, it can actually be quite resistant to the degradation and find its way to the target. The other thing is when you extract it from nature. So, just imagine, I'll give you the example of the peptide that we have that comes from the fava bean,
Hmm.
right? So, using AI, scientists found, oh, okay, we know the shape of the receptor. So we know the shape of the key that would unlock the receptor. Let's give that information to AI and have it comb through the genetic code of the fava bean and see if it's there, or the rice or whatever. So they found it in the fava bean, a 10 amino acid sequence. It's an exact sequence. And so AI says, ding, 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 I found it. It's in that chromosome and it's right here. And so the scientists look at it and go, okay, well, I know which enzymes can break it here and here. Like so, and I know sort of about how stable it's going to be, predicting its amino acid sequence and its structure, its primary sequence. So let's take this plant to the lab and let's extract the protein and then let's use the right enzyme combination, the right temperature, the right time. Let's experiment and see if we can tease out that exact peptide. But and it can be done, and it's done, and that's what happened in this case. But what we found was that the peptide doesn't come alone. Like there's all sorts of hydrophobic ends and hydrophilic ends. Well, what does that mean? It means that other peptides that have negative or positive charges are going to bind to it, and then there's like negative and positive, and so you end up with this kind of like a chaperoned blob, and so you end up with this maybe this powder finally that doesn't just have the peptide of interest, but it seems to be chaperoned or within a matrix of all sorts of other plant peptides and proteins that kind of protect it. Now, what
Okay.
drug companies do, like, right now they're working on an oral GLP-1, right? Well, they're not just they don't just sort of have you eat it. They increase the dose because they know that there's going to be a certain amount sacrificed in the acid and the enzyme soup. And they also might protect it. They might use some technologies that enrobe it and protect it to make it last a little bit longer before it's taken up by the gut wall. So that's what the drug companies do, but nature seems to have already done that. That's why, the peptides that we have, these natural peptides, they're not pure. And you have to use a couple of grams because it's not just the peptide, there's other stuff that comes with it, but it protects it. And, the proof is in the pudding, Scotty, because ultimately then, well, in a human clinical study, does it work? And you can, even before you do it in a human clinical study, what you do is you put that peptide mix into a simulated gastric solution and you churn it. And then you examine it in the proteomics lab and say, well, is it still there? Is it still intact? What have we
Mm.
lost? What's still there? And then you do in vitro studies to show, okay, once we've put it in this gastric solution and churned it, um, does it still bind? Is there enough left to bind to the receptors in these in vitro receptor studies? So there's a lot of really cool science that can validate and verify that the peptide that you're finding in nature survives. And if it doesn't, well, try again. Go find a different structure or a different peptide in nature.
Yeah, that's beautiful. So they've built like a peptide matrix structure that helps it get through and do what it's supposed to do. And they've done I find it fascinating that you take it because I'm not in the science world. So I listen to all that. I'm like, oh, that's really neat. You put it in a simulation of the gastric, what that
Yes.
would be like, and it works there. And then you go do the human clinical trials, and then it was proven to do what it's supposed to do. So
Exactly. Yeah.
That's absolutely beautiful. Well, I want to ask you one last question with peptides before we begin to wrap up here. And you've sort of addressed it through here, but like I'm not a science guy. You name a lot of these, the mTOR, and you have your shark enzymes, and I'm like, I'm gonna remember that, and then I don't even remember them now to tell you what their names are. So just to simplify again, what a peptide is. Like I know there's proteins, amino acids. So just a basic for that person out there that's like barely learning again, just a recap because repetition is key with anything. What
Yeah.
is a peptide?
Yeah. It's interesting. I do try to keep things simple.
Yeah.
I have heard people sort of on the, sort of in the social media circles that do use big words and they sound like, oh man, I cannot refute that guy. He's using terms I've never understood. I try not to be that guy. I try to sort of be simple, but I know that it can get sort of complicated fast. I
Yeah.
am really glad that you asked that first basic question of what is a peptide. So, if I was to start like right at the beginning, like right behind me here, I have a picture of a cell, right? And inside the cell, there is the nucleus, and the nucleus has DNA. And the whole purpose of DNA is to be the blueprint for life. And so, the DNA is this beautiful double helix, and there are these base pairs.
Mhm.
So you've only got G, A, T, and C, right? You've only got four letters in the code. But those four letters, if you put three of them together, like GAT, then it codes for an amino acid. And if you put, and maybe CCC is a different amino acid. So it's quite an incredible and beautiful paradigm that the DNA basically is the recipe for amino acids and it strings them together. So
Okay.
there are, a bunch of amino acids, about 20 that are sort of that the body uses to create proteins. So think of proteins as a string of these amino acids that are sort of lumped together, like a string of pearls. And as I mentioned earlier, because each amino acid has a slightly different sort of characteristic, right? Some are big, some are small. Some of them cause a kink in the chain when you put them together. If you put the right combination together in nature, you can have this beautiful helix. And in fact, when your body creates collagen, it's this incredible triple helix of amino acids. So you've got a string of amino acids that forms a helix, and they all sort of join together, and you have this triple helix, which makes this
Oh, cool.
beautiful, strong collagen structure, right? And so that is an example of a protein, right? And not only one protein, but several that come together to form one of the, I guess, connective tissues of the body. Another trick that the DNA has is that it can encode for a sequence of amino acid that ends up folding in a particular way. So then it becomes an enzyme. And what an enzyme really is it's kind of like the shark. This is all protein, but there's an active site, the teeth, and that active site is actually able to either break down molecules or join them together. So
Cool.
enzymes create and break down structures in the body. They create life. And, that's pretty incredible. And let me just go on a tangent here for a minute.
Yeah.
Vitamins and minerals. So, well, what are they for? They're essential to life. What they are they are cofactors for these active sites in enzymes. That's all they are. So vitamin C is a cofactor for an enzyme whose job it is to produce collagen. Without the vitamin C, the enzyme can't work. That's why it leads to scurvy if you don't get vitamin C. The DNA is creating this perfect enzyme to create collagen, but if you can't give the enzyme teeth, vitamin C, it doesn't work. You get collagen sort of breakdown and disease. So the DNA is producing these, and so you've got structural proteins, you've got enzymes, and you've also got peptides, which are messengers. And so peptides are usually a string of amino acids that's less than, usually less than 50. So
Okay.
less than 50. So some of them have like a globular structure and some just have a primary structure. And their job is to then sort of communicate through the body, activate receptors.
Cool. That helps. That helps
Did I go
simplify
into
it a
too
little
much
bit.
detail there? That's a lot.
I love that. Well, we're about ready to wrap this
But you know,
up.
the simple answer.
Go ahead. I want to hear the simple answer. I think.
Well, the simple answer is, right, it's a string of amino acids and it's going to be biologically active. And it's a small sort of string of amino acids tied together.
A small string or chain of these amino acids that signal something in the body, signal the cell to do something.
Right.
Okay, you are great at teaching it.
Exactly.
I
That's
love
it.
that, Mark.
Cool.
So I have one last question for you. What is like one of the most surprising stories or things that you've seen now that people have been using these natural peptides? Your own personal experience or a story you've heard. What's something that's maybe surprised you? I know you're excited, like, hey, this is cool. I want to dive into this, but what's something that surprised you about seeing people use these natural peptides? Oh, I think we cut off.
Yeah, you remember early in our discussion, I said peptides. Oh, I can hear you just fine. Um, you hearing me okay? Earlier in the discussion, remember I said that I thought that peptides were just sort of observational biology.
Hmm.
But if we can find peptides, the promise is that they are going to see very quick results in the human body, like because they communicate directly with cells. So this is like the answer. So to me, the best story I can think of is in my own life. I've always been a skinny guy. Like
Hmm.
I was a gymnast when I was younger, and that served me well because I was light and lean. And then I came to America, and the kids here are all into bodybuilding. And so they're like buying protein in bulk and they're like doing their curls and they're just getting big and shredded. And I did that and I got stronger, but I never grew muscle. It's
Hmm.
crazy, right? That's just my body type. And I'm 64 now, and my son is doing bodybuilding, or at least he's in a gym class lifting weights. And I'm like, yeah, I'm skinny me. But hey, I'm going to try this peptide. So I tried this peptide and I started gaining weight. But my clothes were fitting the same. Like I didn't have to tighten the belt. I'm gaining weight. I'm like, what? I've never been 180 pounds in my life. And I'm like, I do this simple regimen of like doing pull-ups and dips and things, and I'm like, suddenly I can do more reps, and it's like, and then I can start seeing muscle build. And I was laying in bed one night, and my wife comes up to me and she literally pokes me in the chest, and she goes, "What the hell is this?" And I'm like, I know. I'm like totally growing muscle. This is crazy. So, like in my own life, I'm like, I can see a difference. And what's interesting is like, yeah, I had a little bit of fat around the middle and I'm gaining weight. And I'm wondering, well, how much of that is like muscle and how much of that is like, am I getting fat? But actually, what happened over a period of 9 months is the weight gained and then it kind of dropped back a bit. And then
Okay.
suddenly I'm starting to see my abs like for the first time in 20 years. And I realized what's happening. Yeah, what I think is happening is like I'm building the muscle. When you build the muscle, then you're burning more calories at rest. When you're
Mhm.
burning those calories at rest, it's actually sort of trying to find a fuel source and it will get it from the adipose tissue, the fat. So that little fluctuation that I saw in my weight was actually evidence that I was growing muscle and that it was working. So it's been incredible. I love to be able to see it in my own life. And I love these peptides that we are sharing with our friends, and I am like the strongest advocate, and I use them myself.
I love that. I'm the same way. Like when I researched the science before I first tried them, I was like four times the muscle protein synthesis than over like a whey protein shake. I was like, I'm in, I'm sold. I'm gonna try that out. Like, I want to do this. But the biggest surprising thing to me was so I lead a youth group for our church, and I tried to out throw them throwing rocks into the lake like 4 years ago. And I tore my rotator cuff in three places. I had like scopes done and everything to figure out the problem. And I did PRP injections, if you know what those are. I did dry needling. I did physical therapy a couple times a
Mhm.
week. And
Yep.
I tore it so bad that it hurt to just hang. Like I had to like wear a like use a cast because it just hurt to, even for my shoulder to hang. But with like
Ouch.
PRP injections and the dry needling, all of that stuff. Like I got it to where like I could walk around without pain. And like I can throw a mean spiral left-handed now because my kids all play sports. So I had to adapt and throw baseball left hand, football left-handed. And I've gone to the gym for 15 years. I'm 44.
Wow.
And I got to like, because of that, I couldn't hang on a pull-up bar. I couldn't do a chin up, a pull-up. I couldn't do an overhead press, even though like I healed it with the PRP injection. I didn't do any surgery, all of that physical therapy. I could move it, but I couldn't
Yeah.
hang. There was still some things there. And I'm like, I guess this is just how I am if I don't want to do surgery. And that was 4 years.
Yeah.
And I started taking the peptides to gain muscle. And within about 4 months, I had full mobility in my shoulder and I could shoulder press again. I hit a PR on my bench press. And I'm just
Hmm.
like, what is this? So I think the biggest thing for me is like the reduced inflammation and the repairing of the muscle, the muscle fibers. And I'm just like, that's incredible. And like, I just got to a place where I thought like, this is it. Like, I'm just going to maintain.
Yeah. Yeah.
But now I'm like hitting PRs and hitting the gym hard. And it's funny, all the younger guys and the older ones, like today I had a dad and his 17-year-old come over to my house right before this podcast. And they were like, this fit peptide, you got to tell us how this works because we've seen what's going on in your transformation. And so
Yes.
it's been game changer for me. So to go out and talk about it and share it with others, it just makes sense. So awesome. Well,
It
Mark,
absolutely is. It's so easy to talk about peptides right now.
yeah. And then it's just simply helping them understand the difference between synthetic and natural and how incredible these are. So, well, I know we have a small disconnection, not disconnection,
Yeah.
but a little lag right now. But Mark, I just wanted to say thank you so much for all the knowledge that you gave us. Like, I'm always inspired by how well of an understanding you have of just how the human body works and functions. And I learned so much from you. So thank you so much for all your knowledge today. And I'm just grateful that you were here with us.
Yes, thank you so much for inviting me. I really appreciate it. And like, if anyone wants to get into that nerdy stuff, you're also welcome to come to our podcast, which is called the Peptide PhDs, right? So yeah, come join us on that one as well.
Awesome. I'll link that in the description of the video,
Peptide
Peptide
PhDs.
PhDs, and I'll put it on the Apple podcast as well. And go learn from Mark. He's incredible at sharing about this. Just how often does your show go so that people can know? How often do you guys put up a podcast?
Yeah, every week. So we've got quite a few out already. Yeah, every week we do it every Thursday, and then it's released, onto Spotify and Apple and iHeartRadio and stuff like a few days later.
Awesome. Go give that podcast a follow, and let's continue just learning and educating on how we can best help ourselves and other people. Thank you for joining us on this episode. We hope that you enjoyed the conversation that we shared with you today. We're here to remind you that your family is your most important work on earth, help you feel better, and learn how to earn more income for your family. Make sure to follow Mark and the Peptide PhD podcast. If you're interested in trying these peptides or building a business with natural peptides, feel free to reach out to the person who sent you this podcast. If you enjoyed this episode, please leave a positive review, clip what you like, or share it with a friend. My friend, it's time to level up.